Welcome to Who's in STEM. I'm Ken Ono, your host, and the STEM advisor to the provost and the Marvin Rosenblum Professor of Mathematics at UVA. Our goal is to evoke flights of imagination and wonder by showcasing the cornucopia of all that is STEM at UVA, the marvelous world of UVA science, technology, engineering, and mathematics. Now, I love films. My favorites are Fried Green Tomatoes with Kathy Bates, A River Runs Through It with Brad Pitt, and how about The Shawshank Redemption with Morgan Freeman and Tim Robbins? My guess is that you've seen many of those films, maybe all three. And what ties them together? Well, those three films, they represent slices of Americana, portraits of grit and grace, all set in past times and places. Fried Green Tomatoes, think Whistle Stop Cafe. And it was a story about friendship, courage, and a cafe that becomes a refuge in the 1920s and 30s. A River Runs Through It. That takes place where my wife was born, Missoula, Montana, in the early 1900s. It's a story about two brothers, fly fishing, and a story about great loss. And of course, there's Shawshank Redemption, which is considered one of the best movies of all time. It took place in Maine in the 1940s and 1950s, and, well, it's a story about hope chiseling its way through concrete walls. Well, I also love stories that play with time, not just stories that took place a long time ago. I'm, of course, a huge fan of the Back to the Future trilogy with Michael J. Fox and Leah Thompson. Who can forget Doc Brown's flux capacitor and the flying DeLorean? Pure fun. And that brings me to a more recent film that plays with time travel, Interstellar, with Matthew McConaughey. In that film, Earth is failing, and a secret national mission sends Cooper, an astronaut, through a wormhole to scout worlds orbiting a supermassive black hole. It's called Gargantua. And near Gargantua, well, time runs differently. An hour there equals 7 years back at home. And that forces choices that have heartbreaking consequences. If you haven't seen the film, go watch it. And in the end, gravity itself becomes the message, bridging a gap of years and seconds. Now, Interstellar isn't so far out there scientifically. You might think that time travel is way out there, but Nobel laureate Kip Thorne served as the executive producer and science consultant for the film. And he even fed Einstein's equations into the visual effects pipeline that generated the black hole, that generated the images of Gargantua. And so the images were both cinematic and scientifically meaningful. And the film was anchored in general relativity, where gravity isn't just a force, but it's what defines space-time. It slows clocks, it bends light, and if you've seen the film, you know that it choreographs the dancing of the stars. So that brings us to our conversation today. Black holes and gravity. You see, black holes aren't just movie stars, they're labs, they're real-world laboratories. When black holes collide, they ring space-time like a bell. And at UVA, we're thrilled to have Associate Professor Kent Yagi, a physicist whose work is driving this theory forward. He is cutting edge. So, Professor Yagi, thanks for sitting down with us today.
Thanks. It's great to be here, and I'm so excited to have a chat with you today.
Same here. And I know you're about to race off to a conference in Japan, so thank you for making time in your very busy and hectic schedule. Let's start with the science. I've talked about gravity in the context of films. I've loosely alluded to Einstein and physics. So the basics, what do we mean when we talk about gravitational waves in the context of black holes, physics, and all of that?
Yes, so it all started from Einstein, who first theorized the existence of gravitational waves in 1916 as part of his proposed theory of general relativity, or GR for short. Let me first explain why we talk so much about Einstein. There are three big contributions. The first one is called photoelectric effect, and it proves light has both wave and particle properties, a basic concept in quantum mechanics. The second one is Brownian motion. Collisions of individual atoms, molecules in a liquid causes the random motion of particles inside it. And finally, theory of relativity. which consists of special relativity and general relativity, with gravity related to the latter. GR, general relativity, describes gravity as a property of four-dimensional space-time. Just the usual three-dimensional space plus one time dimension. And the big assumption here is that any object in our universe, such as the Earth or the Sun, or even you who's listening to this podcast today, creates a curved dent in the space-time around it, and when it moves, it emits gravitational waves, which are ripples of space-time.
So let's circle back a little bit. So everybody knows Einstein as this super intelligent physicist whose ideas still drive modern research. You can still win a Nobel Prize for conducting an experiment that confirms or supports one of his predictions. But let's rewind just a little bit. When I was in high school, I took a physics class. And at that time, I was thinking about becoming a mathematician, so I took calculus. And so the names that pop out and were prominent in both calculus and physics were Newton, right? So Newton's laws of gravity famously were used in combination with mathematics to discover planets you couldn't see with the naked eye. You could infer using those laws of gravity the existence of planets like Pluto, although I guess it's been downgraded. Pluto and Neptune, we could use mathematics and observations of planets closer to us to infer the existence. And for me, that was mind-blowing mathematically. But I think, as we know, Newton's laws of gravity are not sufficient for explaining the modern world, which is why Einstein is so famous. So maybe we could talk a little bit about what the fundamental principle is in relativity. A story that I like to tell is that in the 19th century, some astronomers and some mathematicians used Newton's ideas to falsely conclude that there's a planet that orbits inside the orbit of Mercury called Vulcan. So you might know of Vulcan because of Star Trek, but no, in the 19th century, scientists believed and desperately looked for a planet that would somehow have to exist if Newton's laws of gravity was somehow complete. But that wasn't the case. So tell us, how did Einstein's theory of relativity sort of erase this mistake and open an entire new field of physics?
Right. Yes. So until 19th century, people believed in Newtonian physics, and that was perfect. But then, yes, this anomalous Mercury's orbit was found. The problem was that Newtonian physics was only valid when the field is weak. And because Sun is so massive and Mercury is orbiting very close to the Sun, the gravitational field is not so weak. So that's where we have to abandon Newtonian physics and then go beyond Newtonian physics. And that's where general relativity came into play.
And so in terms of gravitational waves, where does that come from?
Yes. So when an object moves, then these object create ripples of space-time called gravitational waves. And imagine you're throwing a pebble onto a pond. Then you will create ripples on water surface. Gravitational waves are just like that. But these waves are extremely difficult to catch, and it took us 100 years since the prediction by Einstein to actually catch these waves. The first detection was made by a detector called LIGO in 2015, and the waves were created by two black holes, each having 30 times more mass than the Sun, moving at half the speed of light, smashing with each other. This was the most energetic astrophysical event observed ever at that time.
So to put that into context, we've heard of things like supernovas. We've heard about things like pulsars, right? Suns rapidly rotating about each other. So tell us, what is a black hole? How rare are they? And how common are these black hole collisions?
Black holes form after the death of very massive stars. For example, if we start with a star whose mass is more than 20 times the mass of the Sun, then eventually it runs out of its fuel and it loses its pressure and it undergoes collapse. During this collapse, supernova explosion happens. Then the remnant that formed is called a black hole. And actually, there's nothing inside black hole. It's vacuum. Except probably at the very center, which is called singularity. And we don't really know what's happening near this single point singularity because general relativity breaks down. And the characteristic surface is called event horizon. And this is the surface where what we call escape velocity of an object is equal to the speed of light, meaning that nothing can escape from inside this black hole because nothing can move faster than the speed of light. And out in the universe, these black holes can collide, can form a binary system. Binary means that black holes are orbiting around each other, the two of them. And because gravitational waves extract energy from this system, these two black holes come closer and closer together until they collide. And when they collide, they produce huge amount of gravitational waves.
So just for baseline data, how many black holes have been observed by scientists in all of history?
Let's see. So there are two different kinds of black holes. The smaller black holes are called stellar mass black holes. They have the mass somewhere like roughly 10 times the mass of the sun. And there's another class called supermassive black holes. They sit at the center of galaxies. So let's see. For stellar mass black holes, you can use X-ray observations, and I don't know the exact number. Probably we know 20 or 50 or 100 black holes, maybe.
Not so many. So the LIGO experiment, which captured a collision of two supermassive black holes, or just two black holes?
Two stellar mass black holes.
Okay, so that's an unusually rare event. So help me understand. First of all, when a gravitational wave hits you, you don't get knocked over, right? So when the scientists recognized and first sensed evidence of this collision, none of us on planet Earth were knocked over. It wasn't like an earthquake. What does that signal look like, and what kind of instrumentation and science is required to confirm something so faint that none of us experienced it personally on Earth?
So the detector is called LIGO, and LIGO stands for Laser Interferometer Gravitational Wave Observatory. There are actually two LIGOs. One is in Washington State, the other one is in Louisiana State. And it has an L shape with each arm length of 4 kilometers. When gravitational waves pass by, they create fluctuation onto these detectors. Now, with the 4-kilometer long detector, the amount of fluctuation caused by these gravitational waves were 4 times 10 to minus 80 meter in size, which is more than 1,000 times smaller than the size of a proton. And this is why Ken was saying that he doesn't remember feeling gravitational waves when this event was detected, because for us, the amount of fluctuation was so tiny, just we don't feel the presence of gravitational waves. And that's exactly why it's so difficult to catch these waves.
Right, there could have been a fender bender in the parking lot, right?
Yeah.
But so as I understand it, not only is the length of the detector important, but it's absolutely critical that there's two detectors so far apart searching for evidence of exactly the same signal.
Yes, exactly. And that's because LIGO is so sensitive that, for example, even somebody walks by the detector, LIGO will know and LIGO will feel it. So in the signal, LIGO has so many kind of noises. So you have to subtract first all those possible noises like seismic noise or thermal noise. And after reducing all those noises, even if you see some signal, then it's likely that those came from astrophysical sources. But we could be more confident if we compare the signals coming from two different detectors. They are far away. And if we see exactly the same signal, then that's a sign that they came from astrophysical sources like two black holes colliding.
And so in real time, the data that's captured in Louisiana and Washington State are cross-referenced, and they look for signatures, and any faint signature that appears at both sites, it's likely astronomical in origin. Is that right?
Yeah, that's exactly right.
So how do you know that there are two black holes colliding as opposed to some other event? What is the signature for a gravitational wave?
Right, yeah. So what we do is that we prepare theoretical waveforms. And by that, what I mean is that, for example, you choose a mass of a black hole and then another mass for its companion. Then we run some simulation and compute gravitational waves. we repeat this for many different combination of masses, or there are actually other parameters like how fast black holes are spinning or how far away the source is. So we basically change all these parameters and then construct thousands of theoretically predicted waveforms. Then we cross-correlate one by one these theoretically predicted waves against the data and see which of the predicted waves matches best with the data. And the best fit wave gives us best fit masses. With the first detection, the masses of black holes were found to be something like 30 times the mass of the sun. And within general relativity, there's no such object whose mass is greater than, say, 3 to 5 solar mass. Mm-hmm. So we know that it has to be black hole.
I see. Now, this work, one of the largest experiments ever conducted in this country, it's an example of big science. It garnered the Nobel Prize. So what about this discovery is it that earned the Nobel Prize? Is it the confirming Einstein's predictions almost spot on the nose? Is it also part the success of an incredible experiment as an example of big science? What are all the factors do you think played into that decision?
Yes, I think it's both. That sometimes gravitational wave detection is called like the last homework from Einstein. Again, it took us 100 years since the prediction by Einstein. And Einstein's theory of relativity has been proven to be correct with many different kinds of tests. Mercury's orbit was one of them. According to general relativity, even light path can bend if it passes nearby a very heavy object. So with this light bending, you can also test general relativity. But because gravitational waves were not detected until 100 years after the prediction by Einstein, that was a huge discovery. And as you said, because the instrument was so sensitive and there's a long history of creating this LIGO detector and then making such huge improvement, they had to reduce the noise by 20 orders of magnitude or something.
Oh.
So yeah, it was a huge achievement and huge discovery. So yeah, all combined worth Nobel Prize.
Yeah. So what should we be thinking now about general relativity? Is the discovery of gravitational waves somehow the final story on general relativity, or are there refinements that continue and are driving cutting-edge research?
Yes, so it's interesting that so far general relativity has passed all the tests being put to it, but from theoretical viewpoint, we know that we have to go beyond general relativity. And that's because general relativity does not go along well with quantum mechanics. Yeah. And the reason is they describe totally different scales. So general relativity describes what happens in the very large scale, like planets and galaxies, by having this space-time to be curved. On the other hand, for quantum mechanics, they describe very micro physics scales, like particles or subatomic particles. And because the scales are so different, it's really difficult to combine these two theories. And if you naively try to combine, then you will have some quantities blowing up, meaning that math stops working. So we know from theory that we have to go beyond general relativity, which is not so crazy if you go back to the history of gravitational theory. We believed in Newtonian physics until 19th century. Then we moved to general relativity, which is more fundamental. Now it's time to go from general relativity to something more fundamental. One strong candidate is called string theory. And string theory predicts that we are made up of some kind of strings. They are
vibrating strings with various properties and many, many more dimensions than 4, right?
Yes, that's right. So depending on what kind of strings you have, what kind of vibrations you have, you can describe different particles, like photon, which is a particle version of light wave, or even gravitons, which are particle version of gravitational waves. So by using gravitational waves, we can actually test whether general relativity is correct or not. For example, we can take general relativity and then do a simulation of two black holes colliding, get the gravitational wave. Now we can repeat the same analysis, but using string theory, for example.
So if we start going into string theory, and as a mathematician, I like the word string theory because there's algebraic geometry, there's number theory. It's involves objects that I think about. But I'm not a string theorist, and I've heard string theorists talk about stringy black holes, and one comes up with models of various kinds of quantum gravity involving stringy black holes, which is the stuff of mathematics. Tell us a little bit about this divide between the theoretical concepts and what we've already observed with these experiments and how that interfaces with your work.
Right. Yes. So what we can do is we can take a theory of gravity that's different from general relativity, like string theory, and then, as Ken was saying, black hole solution could be different from the one predicted by general relativity. So we take those corrections to general relativity into account. Then we run simulation of two black holes colliding. Then we calculate gravitational waves and compare these waves against the data and ask the data which one does it prefer, general relativity or something different like string theory. So by using gravitational waves, we can look for violation of general relativity like string theory. And then we can test general relativity.
And so when you compare the data from gravitational waves with, I guess, models that have been proposed in string theory, I have to believe that most of the models fail or don't do well. They might be interesting mathematically, but in terms of trying to bring the observations of nature in correspondence with the theoretical mathematics, you can't just guess, which is why you need this data. Where's the field today, and what do you predict for the future, and how does it relate to, say, your work?
Right. So far, gravitational wave data haven't found any evidence for violation of general relativity. And if you naively take string theory or quantum gravity, then the correction to general relativity would be something microscopic in scale. But we are using astrophysical scale object to use and test general relativity.
Right. It seems exactly backwards, right?
Yeah,
Right.
Yeah.
So are there experiments on a micro scale that can be, or that we are conducting, that are searching for this evidence?
There are some experiments like tabletop experiments, but still those are not enough to go deep into what we call Planck scale, which is the quantum mechanical scale. So in practice, what we can test is some kind of theory where those Planck scale corrections get enhanced somehow such that it can be tested. Or we can be agnostic and we say that although the motivation is to find theories of everything and maybe the correction is suppressed by Planck scale, still we can be agnostic and then use these gravitational waves to search for some evidence of violation of general relativity. And if we find one, then we can get some insight on which direction to go and then establish theories of everything.
So Kent, thank you. Tell us about your work. What are you working on right now?
So right now, one thing I'm working on is to construct these gravitational waves in string theory, which has extra dimensions. And then because we don't feel those extra dimensions, but gravitational waves can by leaking out to those extra dimensions, we are comparing those gravitational waves in string theory against LIGO's data. And for example, we managed to rule out some of very simple extra dimension model that's motivated from string theory.
The toy models,
yes,
right?
Toy models, yes.
So what does that look like when you say you rule them out? You make predictions based on the theory and they're just completely contradictory to experimental evidence?
Yes, that's right. Yeah, we use this toy model and then compute gravitational waves. And if this toy model is correct, then that means LIGO would have seen some kind of violation of general relativity, which LIGO hasn't found. So that's why we say that we can rule out this toy model.
So the toy models that you ruled out, they involve 7, 8 dimensions, or?
It's we started with 5-dimensional spacetime, which means that there's only one extra dimension. But we found that with this kind of toy model, we can also add any number of extra dimensions, and all of those can be ruled out.
Who are the first to propose the toy models? Are they angry with you?
I don't think he's even alive.
Oh.
It all started with Kaluza and Klein, I
Uh-huh.
think. And they were trying to go from four-dimensional space-time to five-dimensional space-time. And they are trying to what we call compactify the extra dimension, fifth dimension, because we don't feel those extra dimensions. And what happens is that by compactifying those extra dimensions, we can naturally get some field like which mimics electromagnetic field.
Mm-hmm. How would you describe to a non-physicist what we should be thinking about dimensions beyond the 3 or 4 that we experience? I think we all get left, right, up, down, right? We know the ordinary 3 dimensions, and I think we all understand time. We don't know how to go back in time. How would you try to describe, not mathematically, not physically, the mere possibility that there could be dimensions that we just can't happen to perceive?
Right. So let me give you an example. Let's imagine there is a tight rope, and you're walking on this tight rope. Then you can move forward or backward. So it's a one-dimensional system for you. Now imagine there is a tiny creature or an insect living on this tight rope. Then this tiny creature can go in the same direction as you, forward or backward, but it can also go around this rope. And that's because this tiny creature's size is much smaller than the thickness of this rope. So for this tiny creature, it's a two-dimensional system.
Right.
What this example is telling you is that if the size of some dimension is much smaller than yourself, you just don't feel it. So,
very good example. Just from a humanistic perspective, we already see lots of examples where our sensory perception certainly is not representative of everything that exists. So from that perspective, I think we can also say, yeah, it would be absurd to think that our senses are all that is required to perceive the universe. So you're going off to this conference in Japan, a workshop. What's the workshop about?
Oh, it's about the workshop is called something like connecting two infinities, and those two infinities means large-scale infinity and microscopic scale infinity.
X to infinity and 1 over x goes goes to 0 as x goes to infinity, right?
Yeah. So it tries to connect those large-scale physics to a micro physics scale, but of course it has some aspect of gravitational theory or high-energy physics, but it also has some cosmology or particle astrophysics. So it's a very interdisciplinary, broad conference.
So in your work, have you taken a trip out to one of these LIGO centers?
Actually, no. I've never been to LIGO site. I really wish I had a chance, but not for now. There is one gravitation wave detector in Japan, and it's called Kagura. Although I haven't been to Kagura detector, I have been to this mountain where Kagura is buried. And
it's buried?
Yeah,
okay.
Inside a mountain. And there's also other kind of detectors. The famous one is called Kamiokande. That's a neutrino detector, and I have visited Kamiokande.
So question, how many collisions have now been detected by the union of all of the LIGO type detectors? Are we up to 10? I mean, they must be very rare.
You might think they're rare, but so far LIGO has reported more than 200 gravitational wave events.
Oh, so the universe is huge. Yeah. And all of these events are black hole collisions?
Most of them are black hole collisions, but some of them are neutron star collisions, like two neutron stars colliding, and some of them are even mixed. One neutron star, one black hole colliding.
Oh. Do they have a different signature so you can do the math and predict that the waves will have a different signature?
Yes. So black hole, as I said, is mostly vacuum, but neutron stars have some matter inside. So when neutron star gets closer to its companion, it gets tightly deformed. So the shape changes from a sphere to something oblate. And this information is encoded in gravitational waves. And this is quite interesting because the amount of this deformability of these neutron stars due to its companion's field depends on the internal structure of a neutron star, which is controlled by nuclear physics. And the central density of neutron star goes beyond nuclear density. So this super dense environment is something that we cannot realize on ground experiments.
Right.
So we can use neutron observations to infer what's happening in nuclear matter physics.
So these gravitational waves presumably take a long time to reach us, right? So these collisions that have been observed, when did they happen? Was
Like
Einstein alive when they happened?
No.
You know?
Billions of years ago.
Yeah. So it's interesting. So the data that you're collecting happened long before Einstein even developed his theory. So that's kind of poetic, right? So when we talk about time, there are many different perspectives to all of this. So Kent, in the film, it's not time travel in Interstellar, but the heart-wrenching fact in this film is that time ticks along at very different rates, and that's an important part of the closing scene here. But maybe you could tell us another story. Isn't there a famous paradox that you could share with us to clearly illustrate special relativity and this mind-bending concept?
Yes. So there's a famous paradox called twin paradox. Imagine there are two twins. Let's say one is Bob and one is Alice. Now, let's say that Bob is remaining on Earth, but Alice goes on a spaceship and then runs off to some other planet with 80% of the speed of light and then comes back. According to special relativity, if you're moving fast, then your clock will tick slower. So from Bob's perspective, because Alice is moving fast, Bob will claim that Alice ages less. So by the time Alice comes back, Alice is aging less. However, from Alice's point of view, it's Bob that's moving. So when Alice comes back, Alice now claims that Bob is the one who's aging less. Then there's a contradiction, there's a paradox. But actually there's no paradox. Special relativity breaks down if there's some acceleration. So Bob is staying on Earth, there's no acceleration. But for Alice can move 80% of the speed of light, but then when she turns back to Earth, she has to have some kind of acceleration. And that's where her claim breaks down. So the correct answer is the Bob's frame that Alice is aging less than Bob.
So here at University of Virginia, we have a group working on gravitational waves. Tell us about the group.
Yes, so another professor working in gravitational wave physics is Professor David Nichols. Mm-hmm. So we collaborate. And we also have Professor Diana Verman, who's a string theorist. So we collaborate on projects. And also I have collaboration with outside of physics department. I have collaboration with Department of Astronomy, as well as National Radio Astronomy Observatory. So we have like joint group meetings, or we sometimes write papers together.
Oh, that's great. So for students here at the University of Virginia, undergraduates or graduate students who might be interested in learning more about your group, how can they get involved?
Yeah, so my general advice is to keep curiosity broad. When I was a student, I was mainly focusing on black hole physics, and I wasn't so much interested in nuclear physics or neutron stars. But I was lucky enough to hear a lot of works on neutron star physics. And then it eventually made me find some discovery on neutron star physics. So you never know what would be beneficial to your career. So just study broadly and open your curiosity wide.
And are there seminars or colloquia? How can students get involved? Can they do research in your group?
Yes. So there's a gravity seminar organized bi-weekly, mm-hmm. and there are colloquiums, and if students are interested in getting involved in research in general relativity, then sometimes I ask them to first take general relativity course. There is an intro to general relativity course offered at UVA Physics, and undergrads can take those. But there are also projects that can be done without having solid understanding of general relativity, like solving some differential equations numerically. So it's more like computational effort.
Okay. Well, Kent, time is running short here, and I have two questions I really want to ask you. The first is, tell us about your path. I think you're originally from Japan. How did you end up here at the University of Virginia?
Right, yes. So I grew up in Japan, and I got my PhD from Kyoto University. And when I entered the university, I didn't know about gravitational waves, but when I was an undergrad, I got a chance to hear a public seminar by a grad student. And then I was fascinated, and I thought this is what I want to do, because I learned that with this single messenger, we can learn so many different kinds of physics and our universe. At that time, it was like 2005 or 7 or something. So gravitational waves were not detected. And some other groups like Cosmic Ray Group was making fun of us that why we are studying something that they thought would never be able to be detected. So I was very happy that they are proven to be
something
wrong.
like SETI, the search for extraterrestrial intelligence, right? People who are looking up at the sky hoping, but maybe one day that'll happen. So after your undergraduate degree at Kyoto?
Yeah, I moved to a grad school at the same university. And then when I was fourth year in my PhD program, I went to a conference in Mexico City. At first, I was hesitant to go because I heard the city was rough, but I decided to go. And then I saw a researcher whose papers I read a lot. So I introduced myself, and it turned out that he was the referee of my first paper. So he said he knew me, and he said he's going to hire postdocs, so I should apply. I did, and then I was lucky enough that he could hire me. So I started working at Montana State University in Bozeman, Montana.
In Bozeman. So what was that like going from Japan to Bozeman, Montana?
Yeah, so Kyoto is a big city with
several million people.
Several million people.
The whole state of Montana doesn't have 1 million people.
Yeah, Bozeman itself only like 30,000 or something. Yeah, so it was a completely different experience. But then at first, before moving to Bozeman, I wasn't sure if I'm going to like the life there. But I really loved the life.
The cowboy life.
Yeah, beautiful mountains, wild animals. Yellowstone National Park was only 1.5 hour drive, so you can just go there on weekends.
Yeah. And so after your postdoc,
Yeah, so that was my first postdoc. Then I moved to Princeton University to do my second postdoc. That was around 2015 when the first detection by LIGO was made. And now everyone, all universities, including UVA, got excited. And at that time, there were nobody working in my field at UVA Physics. So the department decided to hire somebody. So there's an opening for the position. I applied, and then I was once again lucky enough to get the offer.
Yeah, your story somewhat parallels mine. I finished my PhD in 1993, last century. And the work that I was doing at the time, I think many people would have considered it backwaters mathematics. And it involved objects called modular forms and Galois representations. It's a technical thing, but those are just the words. And a few months after I defended my thesis, these objects were used to solve a problem called Fermat's last theorem, which at the time was in the Guinness Book of World Records as the most famous open math problem. And it was extraordinary to have been spending 4 or 5 years kind of almost in isolation working on objects and have the whole universe of mathematicians overnight wanting to learn about it. And that's sort of, I think, mirrors your experience. We're very lucky. So thank you for sharing that. Well, we do have to wrap up, Kent. my last question, fun fact. Tell us something fun about you that maybe even people in your department might not know.
So as a fun fact, I'm collaborating with some of the members at UVA Game Development Club to create an online game about general relativity and gravitational waves.
Oh.
The idea is that a player becomes a tiny creature on a tiny spaceship, and then they are asked to collect all the particles in the universe, and the goal is to make themselves collapse to a neutron-star black hole in the end. But sometimes there are gravitational waves passing by, wobbling the space-time, and then preventing them from collecting particles. It's still under development, but I really hope that we can complete it soon. So that
is there a name for the game?
It's called Gravitational Wave Surfer.
So is the character like literally on a surfboard in space?
No. Right now the character is in a spaceship. And
Okay.
it's wobbling when gravitational waves pass by.
Okay. All right. Well, Kent, this is super. Thank you very much for taking the time to be with us today. As you can see, as a mathematician, I find this work fascinating. And I think for our listeners, thank you for sharing in a very comprehensible way this deep and important work. I'm Ken Ono, STEM advisor to the Provost and the Marvin Rosenblum Professor of Mathematics, and you've been listening to Who's in STEM.
Who's in STEM is a production of WTJU 91.1 FM and the Office of the Provost at the University of Virginia. Who's in STEM is produced by Benjamin Larson, Katie Nichols, and Ria Verma. Our music is composed and performed by Robert Schneider and John Ferguson of Apples and Stereo. Follow us on Instagram, listen and subscribe to Who's in STEM on Apple Podcasts, Spotify, or wherever you get your podcasts. We'll be back soon with another conversation about scientific and technological innovation at the university.